This conference will now be recorded.
Okay, good morning all. Hope that I am audible. Last class we are discussing about the decoding of the linear block code, which is termed as that syndrome decoding. And yesterday we have solved a problem that is generated the linear block code from a given generator matrix or from a parity check matrix. That is which is denoted as G matrix or H matrix that we have seen. Once it is obtained, it is given, we are able to generate or construct the linear block code. And once the all the code words are written, all code vectors are written, we are able to find the minimum distance, d minimum of the code, and therefore from that parameter, that by making use of that parameter d minimum or minimum distance, we can comment about, we can say the error detection and error correction correction and error detection capability of that particular code. And then said that the important property of that code, that is that which is make use of in the for the purpose of that decoding, which is termed as syndrome decoding. That is x into h transpose is 0. That is, if we multiply a valid code vector with the h transpose matrix, then we get a 0 vector. It is a 0 vector having q number of zeros, where q is equal to n minus k. That is that extra bit, that check bits we are adding to the message bits for the purpose of error detection and coding. Therefore, we can take it as the y as a received vector or the received code word. Then if we multiply the y with the h transpose matrix, we get a 0 vector or a non-zero vector. Then that 0 means that s equal to y into h transpose. S are 0 for when we can say no error in the output, that is x and y are same, that is the transmitted word x is received at the receiver end, then we get no error. The another possibility is y is some other valid code vector other than x. This means that more errors are occurred, and that received code word became another valid code vector. That is, we are transmitting a code vector x1 and we are receiving another valid code vector x2. That is, some error occurred and it became another valid code vector. Then since it is a valid code vector, if you multiply with the multiply that received vector with the h transpose matrix, we get a 0 vector. Therefore, in that case, we are not able to detect the transmission errors. Then we can consider that is that how we can detect the error from that syndrome vector and the error vector, that is that detection and the correction. Here we are here we have an n-bit error vector, n-bit error vector. Therefore, for a 8-4 block code, 8-4 linear block code, the error vector will be a 8-bit vector. And this error vector actually represent the position of the transmission errors in y. That is, that error vector represent in which bit positions are the error in the received vector. For example, take x equal to 10110. That is a 6-bit code word here. We are transmitting a 6-bit code word. That is the linear block code n equal to 6. Therefore, that code word is a 6-bit length code word. Sorry, here it is 5 only. Sorry, 5. 10110. A 5-bit code word here. and the received code word is 10011. Okay, then we can say first bit there is no error, second bit no error, third bit an error occurred. Actually the actual bit is 1, but the in the received code word it is 0. Therefore in the error vector that is represented by that bit 1. Then a fourth bit transmitted is 1, received is 1. Then we can write the 0 in the error vector. Then 0 is the fifth bit. In X, the transmitted bit is 0 and the received bit is 1. Then we can represent it by a 1. Therefore, in that way, we are writing the error vector. Here in the third and the fifth bit, an error occurred. Therefore, we represent a non-zero entries. That is here 1. Non-zero entries represent the errors in Y. For here X and Y, here third and fifth bit are in error. Therefore, we represent the error vector with non-zero entries in Y in that particular bit position in which the error is occurred. Therefore, here in the error vector, that fifth and third bit are 1. All the others are 0. For here, a 2-bit error occurred. Therefore, the corresponding error vector is represented here. That is about that error vector. Then detecting error. This we can say that is using mode to addition. We can write y equal to x XOR e. That is here x is the transmitted word and e is the error vector. We can consider the previous case. If we do the mode to addition or XOR addition of x and y, therefore first bit is 1, here it is 0, therefore result 1, 0 0 0 1 1 0. That is here an error is occurred, therefore the third bit is changed. Then 1 plus 0 1, 0 plus 1 1. Okay, therefore we can write x XOR e equal to y. That is, if we add that transmitted code word or transmitted code vector with the error vector, the result will be that y. Similarly, we can write that x equal to y XOR e. If we add the received code word with the error vector, that is y XOR e, 1 plus 0 1, 0 0 0, 0 plus 1 1, 1 plus 0 1, 1 last bit. In y it is 1, in error vector it is 1, therefore 1 plus 1 0. This here we are using mode to addition. Therefore we can also write that x equal to y plus e, that is y XOR e. That is here that this represent the mode to addition. Then here we have equation S equal to y into h transpose. That syndrome vector can be obtained by multiplying the received code vector with the h transpose matrix. For S equal to y into h transpose, then x that is here we are substituting for that y is equal to x plus e. For x plus e into h transpose and expanding x into h transpose plus e into h transpose, we get e into h transpose. Therefore we can see from the property of this linear block code that syndrome vector is equal to e into h transpose. Here e represent the error vector. That is, from that error vector is nothing but a vector which shows a non-zero entries in the bit position where the error is occurred. That is, error vector is nothing but the in that vector non-zero entries at the positions where the error is occurred. If it is a 7-bit code word, then in the first and last bit error occurred, then we can say that corresponding error vector is the first bit will be 1, last bit 7th bit will be 1, all the remaining bits will be zeros. Therefore here here we have shown that syndrome vector is equal to E into H transpose. That is, if you multiply the error vector with the H transpose matrix, then that will give the S, that syndrome vector. That is, this relation shows that the syndrome depends upon the error pattern only. Okay, that syndrome vector syndrome depends upon the error pattern only. That is, it is independent of the code word. If we take any of the code word, then that syndrome vector depends only on the error pattern. That is, the bit position in which the error occurred. We have this relation S equal to Y into H transpose, and shown E into H transpose, that S equal to E into H transpose. Here H transpose is fixed for a particular generator, particular linear block code. Then that E, here it is a error vector. That error vector means the vector which shows the bit position in which the error is occurred, and here S equal to E into H transpose. Therefore we can conclude that the syndrome depends upon the error pattern only. It is independent of the code word. If you take any code word, uh, it depends on that syndrome vector depends only on the bit position in which the error occurred. Then you can take this example. That is, a H transpose H matrix is given. Here it is a problem. It is H is given. That is the parity check matrix. We know that initial part will be our P transpose matrix, where P is that part of that submatrix of the generator matrix. Therefore here that initial part, that 3/4 matrix, is the P transpose. Then that remaining part is an identity matrix for the order Q. That is the general structure of the parity check matrix. And from this, that is here, only the parity check matrix is given. We can generate the all the code word, and we can detect the its minimum distance. Then we can find the error detection and error correction capability of this code, etc. And if we are given a code word, a received code word, we can find whether it is a actual transmitted word, or if some errors are occurred, we can find the uh, error, and we can correct that error. There is a limit to that error, how much error can be detected, and how much error can be corrected. Okay, from this H transpose matrix, here H transpose H matrix parity check matrix is given. Here we can say n equal to 7, k equal to 4, q equal to 3. It is here, it is a H matrix parity check matrix of a 7/4 linear block code. Then we know the syndrome vector is a q bit vector. Is we will get a syndrome vector where the number of elements in that syndrome will be q. Therefore here in this case it will be 3. And out of that there will be different syndrome vectors. We can say with q equal to 3, here q equal to 3, 2 raised to 3 minus 1, that is here equal to 7. 7 will be non-zero syndromes. It is here we have q equal to 3. Then the syndrome vector is a q bit vector. It is here there are different possibilities, that 0 0 0 0 0 1 up to 1 1 1. Therefore if we avoid that zero vector, that is all the elements are zeros, that is 0 0 0, there are 7 non-zero syndromes. Okay, that syndrome vector non-zero value will be 7 if with q equal to 3. And here error vectors, we know error vector is 7-bit word. Error vector will be a 7-bit word. And if we consider only single bit error vector corresponding to single bit error, that is, the error is occurred in uh, only in one bit position, then we can have different error vectors like this. First bit is 1, all the remaining bits, that is 6 zeros. Then second bit 1, all the remaining bits are zeros, like that. If the error is occurred in the last bit of the any of the code word, then the corresponding error vector will be 6 zeros and last bit equal to 1. Okay, like that. That is, here we have said that there will be 7 non-zero syndromes with a q equal to 3, and that error vectors corresponding to single bit error. If only a single bit error is occurred, then the error vectors will be like this. That is, any of the bit will be 1 out of that 7 bit. That 7 bit is the there will be 7 bits in the error vector. If we are here we are initially considering only the single bit error, then the corresponding error vectors are here. Then now we are finding the product E into H transpose. You can do this. That is, take the first error vector. That is, the error is occurred in the first bit. Then 1 0 0 0 0 0 0, that is the error vector. It is multiplying with the H transpose matrix. Then the result we get 1 0 1. That is, here 1 into 1 plus all the remaining bits are zeros. Therefore 0 into 0, different value, it will be 0. Therefore 1 into 1, the first bit is 1. Then similarly here 1 into 0 plus 0 into 1, 0 into 1, like that. Therefore we get that second bit 0. Then third bit 1 into 1 1, 0 into 1, 0 into 0, 0 into 1, etc. All are doing that arithmetic, mode 2 arithmetic, mode 2 addition or XOR addition. Therefore we get 1 0 1 as the syndrome vector. Okay, it is the syndrome vector for the first bit error. That is, here we have taken the error vector corresponding to the first bit error. Then we have got 1 0 1 as the syndrome. Okay, then if we do like this, take the second bit error, that syndrome vector, error vector corresponding to the second bit error. That is, here 0 1 0 0 0 0 0, this particular one. If you multiply with this error vector with the H transpose matrix, we will get 1 1 1 as the syndrome vector. Similarly, if we take the error vector corresponding to the syndrome error vector corresponding to the third bit error, we get 1 1 0 as the syndrome vector. Okay, that is, we can see the syndrome vector obtained corresponding to the first bit error is same as the first row of the H transpose matrix. Similarly, syndrome vector for the second bit error will be same as the second row of the H transpose matrix. That is, it will we get 1 1 1. If it is if we calculate the syndrome vector corresponding to the here it is seventh bit, then the syndrome vector will be 0 0 1. That is, it is a seventh row of the H transpose matrix. That is, if it is first bit error, then the syndrome vector will be first row of the H transpose matrix. If the error is occurred in the second bit, then the syndrome vector obtained will be the second row of the H transpose matrix. Therefore, we can make use this method that for the error detection. Initially, calculate the syndrome. using the relation S equal to Y into H transpose. It is a received word is given. We have that generator matrix or any P matrix or H matrix, anything will be given, and the received word is given. We are able to write the corresponding H transpose matrix, find the product Y into H transpose. Then if it is 0, we have got that product Y into H transpose a 0 vector, then means no error occurred. That is, the received word and code word are same. There is another chance, that is more errors are occurred and it become another valid code word. Okay, anyway, if it is 0, we can say X equal to Y or Y equal to X. That is, the transmitted word and the received word are the same. Anyway, here calculate this syndrome, that is, find the product Y into H transpose. Then second step is check the row of H transpose which is same as S. Check the row of H transpose. Is we have got a qubit vector. Compare that vector, that non-zero vector obtained, which is same as the which row of the H transpose matrix. Okay, compare with the H transpose matrix, different rows of the H transpose matrix. Then for pth row of H transpose, if it is same as the pth row, then we can say pth bit is in error. That is, if it is sixth bit, that is once we have calculated the Y into H transpose matrix, then we have seen that vector obtained is same as the sixth row of the H transpose matrix. Then we can say the sixth bit is in error. In the received code word, sixth bit is error. Similarly, if the received code, the product Y into H transpose is same as the fourth row of the H transpose matrix, then we can say the fourth bit is in error in the received code word. For in general, we can say if the Y into H transpose product is same as the pth row of H transpose matrix, then pth bit is in error. Then, okay, we have identified that error position in which the error occurred. Then we can correct that error by using the relation X equal to Y plus E. That is, do the XOR addition, mode 2 addition. Take the received code word and take the corresponding error vector. Here we are saying that single bit error. Therefore, anyway, we are able to write the error vector corresponding to that error position. If we are identified that error is in the sixth bit for a 7-4 block code, then take the sixth bit 1 and all the remaining bits are 0 as the error vector. Then adding Y plus E give the actual transmitted word. That is, once the error is detected, by adding the error vector corresponding to that particular error with the received code word, that will give the actual transmitted word for X equal to Y plus E. And here hope that you have got the idea how we can detect and correct that errors in a linear block code. And okay, before going to a problem of that decoding or error detection and error correction, Hamming code. Hamming codes are NK linear block code which satisfy the following condition. That is, we can say it is a linear block code which satisfies certain criteria. Hamming code, that is, number of check bits QE greater than or equal to 3. That is, that redundant bits or check bits, that extra bits we are adding for the purpose of the error detection and correction is 3 or greater than 3 for a Hamming code. Number of check bits, that is Q, that is that n minus k is greater than or equal to 3. Then block length, n equal to 2 raised to q minus 1. Block length n equal to 2 raised to q minus 1. Then the number of message bits k is equal to n minus q. It is actually in general for a linear block code. Anyway, minimum distance, it is important. D minimum equal to 3. For a Hamming code, that minimum distance D minimum equal to 3. I say the most important criteria which satisfy all others are in general for a linear block code, where q is greater than or equal to 3 and the minimum distance of the Hamming code equal to 3. And therefore, since the minimum distance equal to 3, that is, we say a linear block code satisfying these criteria. Therefore, here we have seen that for a Hamming code, that minimum distance equal to 3. Therefore, Hamming codes can be used to detect double errors or correct single errors. We are able to detect double errors or correct single errors. That is here. That is here. If it is a single bit error, we can uh, properly identify the bit position in which that error is occurred. Therefore, we can correct. And that double errors correction detection means that is that syndrome vector will be a non-zero, but we are not able to identify the correct bit position in that such case. Anyway, for this Hamming code, that D minimum equal to 3. Note that using Hamming code, we can detect double errors and correct single errors. Okay, next we can go for a problem. It is for a systematic linear block code. The three parity check bits are given by, please take this, that C1 equal to D1 plus D2 plus D3. Actually, it is mode 2 addition, XOR addition. C1, that is, we have given the equation for the check bits. Here, this D1, D2, D3, etc. are the message bits. That is, check bits equation for the check bits are given. Okay, equation for the check bits are given. C1 equal to D1 plus D2 plus D3. C2 equal to D1 plus D2. C3 equal to D1 plus D3. And question is construct the generator matrix, construct the code, determine the error correcting capability, decode the received words. That is, here the received words are given 101, 100, and 000110. That is, two words are given. You will have to decode that received word. You will have to identify if any error is occurred or not. If error is occurred, if it is within the error correcting capability of the code, then correct that particular error. Okay, hope that you have taken this equation question, that is equation for the check bits. C1 equal to D1 plus D2 plus D3, C2 equal to D1 plus D2, C3 equal to D1 plus D3. Then from this, we can write the generator matrix, H matrix, etc. For that, we know C equal to MP. That check bit equation, these equations are obtained by multiplying the message bits with the P submatrix. Actually, this C1 equal to D1, D1 plus D2 plus D3, C2 equal to D1 plus D2, C3 equal to D1 plus D3. This is obtained from this equation. The check bits C is equal to M into P. Therefore, from this, that is here, M is equal to the check bits D1, D2, D3. This therefore D1, D2, D3 plus P. We have obtained this equation. Therefore, from this we can write P is equal to, since C1 depends on all the message bits D1, D2, D3, Therefore, first column of the P matrix will be, all the elements will be 1. There 1, D1 plus D2 plus D3. All the message bits are present there. That is, first check bits depends on all the 3 message bits. Therefore, first column elements, all the elements will be 1. Then only, that is multiplying D1 into 1 plus D2 into 1 plus D3 into 1. That expression for the first check bit. Then take the equation for the second check bit, C2, D1 plus D3. Therefore, first and second element of the second column is 1, the third element is 0. Then only D1 into 1 plus D2 into 1 plus D3 into 0. That is the equation for the second check bit, C2 equal to D1 plus D2. Similarly, we can write the third column of the P submatrix from this check bit equation, C3 equal to D1 plus D3, 1, 0, 1. Okay, therefore here we have obtained the P submatrix from this check bit equation. Usually in the examination, or this equation for the check bits will be given. You will have to write the generate matrix, H matrix, etc., and generate construct the code, and all the other factor parameters will have to be find out. Okay. Therefore, once the check bit equation for the check bits are given, we are able to write the P submatrix. Then we know the general form of a generator matrix G is, initial is an identity matrix, then the P submatrix. Therefore, here the generator matrix is written 1 0 0 0 1 0 0 0 1. That is an identity matrix of the order K. Then the P submatrix is written here. Then I am not going to the that is, here generator matrix is given. Construct the code. You can do that. Prepare that table and write the complete code. It is message bit is there are 3 message bits. Then we get 8 different code word corresponding to 8 possible messages. Once that codes are written, we are able to error correcting capability. Find the weight of the code, from that determine the minimum distance of the code, then find the error correcting capability, and last part is decode the received code words. 2 code words we will have to be decoded. Only I am written given that last part. That is, for the decoding purpose, we will have to consider that H transpose matrix from the G. Once the H matrix is obtained, sorry, once the P matrix or G matrix is written, we can write the H matrix. Then H transpose matrix can be written. That is, we know that H matrix has a form P transpose IQ. P transpose IQ. Okay, P transpose IQ is the H matrix, and for that H transpose matrix, here the top part will be P matrix. We are taking the transpose. Therefore, this initial part 3 by 3 will be that P matrix itself, then an identity matrix of the order Q. Therefore, anyway, from this P or G, making use of this P and or G, we have written the H matrix and the H transpose matrix. That is, we are needed for the purpose of that decoding. Then first select the first code word, received code word given, y is equal to 101100. We will have to find the product y into H transpose, y into H transpose. If we find the product y into H transpose, you will get 110 as the product y into H transpose. Take this given code word, received word y, then find the product y into H transpose. You will get 110. Here compare with the H transpose matrix. It is same as the second row of H transpose matrix. Similarly, in the case, it means that error is occurred in the second bit. Therefore, we can correct that error by simply changing the second bit. For 0 must be replaced by 1. That will be the corrected vector. Then similarly, y is equal to that second given received word. Find the product y into h transpose. Again, we have got 110. It means that error is and that 110 is same as the second row of the h transpose matrix. Therefore, we can say the error is occurred in the second bit position in both cases. Therefore, the error vector corresponding to that error in second bit position is 0 1 0 0 0 0, a 6-bit vector in which the second bit is 1. Okay, in both cases error is occurred in the second bit, therefore corresponding error vector is written here. Therefore we can correct that error by simply adding that received code word. First take the received code word, that simply changing the second bit, we will get the answer. Anyway, that procedure we will have to, in order to implement a particular circuit or like that, for this purpose we will have a method. Therefore add the received code word with the corresponding error vector for x equal to y plus e. That will give the correct vector. Okay, uh, that is the method of the decoding. I think we can